take a look at this project live, and I'll get the instructions here. This is 127, and we want to do the SEH project, which is this one. Now, I wrote an old version for Windows Server 2016, and yesterday or the day before I updated it to Windows 10, so I think I'll stick to that one, because I used to use a Server 2016 all the time, and now I'm switching to using the Flare VM, which is very nice and based on Windows 10, and I think I'm going to continue to try to just replace all the projects in this class with ones that work on the Flare VM. So that's what we've got here. Let me just close this. So I just took a Windows 10 VM, and it's got the Immunity Debugger on it. And let's try closing all this junk. Okay, so I'm going to run the Immunity Debugger as administrator. And then I'm going to run the same thing we've been exploiting, which is vuln server. So it's file, vuln servers in my frequently used list. And when I run it, it's now running. So it's listening. It'll pop up a box showing that it is listening. I think, by the way, I can make the font bigger to make it readable. Yeah, so it's waiting. Now I need my address, so I'll open another command prompt and do ipconfig. Okay, so this is 192.168.11.7. Now I've got a Linux box running over here. So let me just use the desktop, the console briefly. I just want to do an IP address in here. This is 192.168.11.6. All right, I want to get in here by SSH because it's easier to use. So I should have a terminal somewhere over here. Okay. So, good, that looks right. Debian. Okay, so there's my Linux box and there's my Windows box, so I can test it with netcat 192.168.11.7 on port 9999. And then see, I have vulnerable servers, so my networking is okay and I can reach my box. That's all I want to do from here. So now I'm going to go into my 127, and this is project ED319. So, all right. And okay, so the first thing we have to do is find an overflow to exploit, and I think I gave you one just to start from here in the project. Yeah, so that's this SEH1. All right. So here, I connect to my server on port 9999, and I just send 3551 A's, and then enough prefix to make total length 4000. And then I send the prefix plus BCDE plus the postfix. And, you know, I skipped the fuzzing step, which we could have done, which you did in an earlier project where you try attacking different things. The thing is, we're attacking the gmon function here. It turns out, remember, there were about 8 keywords you could send this program, and gmon was one of them, followed by a couple of punctuation marks. Then you can send an attack. So this will overflow something. So let's run that, SEH1. Go back here and look at my debugger. It is running. Okay, so if I run SEH1, it now has an access violation. So in this case, it creates some kind of error. And if I look at the exception handler, I can just view SEH chain, and in there I find the BCDE. So I've got an overflow. I put the data in a string, and I was able to hit the exception handler itself. So now it is got an access violation, so it hit the exception handler and then triggered some kind of exception. So I can step into the exception. If I go back to view CPU, to step into the exception, I think it's just Shift F9 I want to hit. Let me check my instructions. That would make sense. Yep. Should logically be Shift F9. That's what I'm going to do. Yeah, Shift F9. Good. So Shift F7 will just take one step. Shift F9 will just pass the exception back to my program, so it uses the exception handler. And when I do that, It then runs, and now it has an access violation when executing that number, which makes perfect sense because I wrote into the exception handler chain BCDE. And now it tried to execute BCDE. So the point is here, I have now found that I can control the instruction pointer. I can put characters under my control into the exception handler, and when the exception hits the code, it will try to use this as an address. So that's a good start. So now the next step is, let's take a look at SEH2. So the next step is to execute some code. So what I'm going to do is here, where, all right. Now I think we need to use vuln. Yeah, we need to use Mona now. All right, so what we need to do is we need to find a pop return. And we can see that because, notice right here, this is the stack at the point of the crash. This goes somewhere, this goes somewhere. The third thing down goes to code under my control. There's the BCDE. So if I do pop return, it will move the instruction pointer and try to execute these 4 bytes. Then it will hit the BCDE, which are bytes I injected to control the instruction pointer. So I can run code, but I can only run a program 4 bytes long. Because the structure of this is, that's where I am. I'm 4 bytes before the instruction pointer where I need to make this point to pop return. So that is pretty tight. So this is why we have to perform a stack pivot. So the first thing is to find a module with a pop return in it that's going to have fixed locations. So as usual, we do bang Mona modules. And we need to find a module in the program that is not going to move. So we want to find ones with rebase and ASLR false. Uh-oh, what's going on here? Looks like I've somehow confused the graphics. Let's try shrinking things and bringing them back. Right. This is, as usual, a failure of VMware tools. There we are. Good. Okay. Okay, there we are. All right, so I need to have rebase and ASLR equal to false. That would be best. Rebase I might not need to have false because rebase doesn't always take effect. But I definitely want ASLR to be turned off or the code will be randomized all the time and it'll be really hard to find anything. So there's only 2 candidates without ASLR, and they're the same ones we saw before. They're the ones that are running old code, which is vuln server itself and its library that came with it, essfunc.dil. And vuln server itself is loaded at 00400,000 like always, so all the addresses in vuln server have null bytes in them, and I can't use them. So the only thing I can use is this one, essfunc, and this also has safe SEH false. So that's where I got to do the ones in that module. All right, now in order to find the pop return, I need to use Mona to find stack pivots. And it'll find them, and it'll write them to where it puts logs. So you have to go into Option Appearance to find out where it puts the logs. And it's one of these tabs, directories. Yeah, that's where it puts them. C, Program Files, x86, Immunity. And you have to be running it as administrator, or it won't have the permissions to write to that directory. So you can now find the gadgets. To find the Mona gadgets in that function, you run this, Mona ROP minus, and this is the function, module essfunc.dil. So this will find the return-oriented programming gadgets in that function. And if I look in the log, it will tell me the ROP generator is finished, and it wrote several things, stack pivots, ROP suggestions, and other things. And this is called a stack pivot, where I just want to get back to the stack. So all I need is the stack pivot .txt file in that directory, which is C, Program Files, x86, Immunity. And now in here I will find a stack pivot text. So when I run that, I will see the stack pivots that exist. And here's information about the modules, and here's the non-safe, say, protected pivots. And as you can see, the first one is probably fine. The first one, the only thing I care about is it doesn't have forbidden characters in it. 6250 10B4. It doesn't have a null byte, which is all I expect, and that will have pop pop return. It's a fairly common thing. There are quite a few pop pop returns, and any of them should do, but that's a good one, 6250 10B4. So that's it. Now I can make an attack using it. So here, if I look at, that's what I've got right here. This is it, 6250 10B4. So I change the number of A's before this by 4. Then I insert my code to execute, which I'm going to do nop, 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 break. Those are the 4 bytes. Remember, I can run a program, but it can only be 4 bytes long. So the first thing I'm going to do is just run 3 nops and a break just to see if it works. And here's the code, here's the address that points to that, so that's it. Then I just make the total length 4,000. So this is a small step forward. So let's run that in the debugger. So it's go back to the CPU and debug restart. And it's loaded but paused, so I have to run it. Okay, and now I run that thing, which is SEH2. And it gives me the access violation, which I expected. And now if I view the SEH chain, it shows that address, 6250 10B4. And if I go examine that, I can follow that address, say, in the stack. And here I have my 909090 C2. So it's going to, I was expecting to see the pop pop return. Let me just view my SEH chain. 6250 10B4. It went there and followed it. Okay, but if I want to look at 6250 10B4, which I kind of do, let's go back to here, view CPU, and I'm just going to right click, go to expression 62. Oh good, 6250 10B4. It's too small to see, but that's what's in there. Yeah, this is what I wanted to see, pop pop return. So if I use Shift F9 to run code, it's going to proceed, and then it's going to jump to the pop pop return, and then it's going to go back here and hit the code I put in. So that's where we are. If I roll it back a bit, you can see here's the A's, here's the not 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 break, here's the 6250 10B4, which the debugger is misunderstanding as code when it's an address, and here's the X's I put after it. So I have proven that I control the EIP. I can jump to a stack pivot and it will accept it. It doesn't have anything in my way like safe SEH or SE-hop. And I can execute code here because I was able to do the nops. If this was not executable, it would have stopped at the nop with an exception. So now I know I can run code. Now I just have the minor irritation that 4 bytes is not a big enough code to make a shell. So what you have to do is you have to pick some more careful assembly language code to execute that will fit in the space that's available. And there are several ways to do it, but the way that worked out best was, is this the one? Am I in the right place? Yeah, this one here. Yeah, and so then I guess I made an extra credit down here, but anyway, the point is you have to go look at your instructions, and you have to choose instructions that will work. And it turns out that if you want to fit it in only 4 bytes, the instruction that will work is jump rel 8 is 2 bytes long. The only choices available are jump relative 8 and jump relative 32. And so the second item is only available in the 32 is operating 16-bit code, so we can't do that. So the only thing we can use is a jump relative 8 because we only have 4 bytes. We don't have the 5 bytes we need to jump a relative 32-bit address. So we can jump, but we can only jump a number of bytes that fits in an 8-bit number, which means from plus 128 to minus 127 or so. So I can jump back, but only by about 128 bytes. So what I'm going to have to do is this one here, put shellcode before the SEH bytes, go pop pop return, put a jump here to jump backwards a bit to find the shellcode. So it's going to take 2 jumps, a short jump to go back 10 bytes, and then a long jump to go back 450 bytes. So that's what it is. And that's what the code looks like that does it. This is a thing that jumps back 8 bytes, EBF6. This is a NOP and a break. It's going to break a couple times just so I can see it. And I used to have one where you go all the way to make one that will automatically run. Here I stopped at this one that has breaks so you can see it go. So we're going to see it take the original address and do a stack pivot to get back to code under our control here. Then it's going to do NOP break so we can see it. Then the F6 EB is jump back 10 bytes. So then it's going to go down here and it's going to be again NOP break. And this is the 5 bytes it takes to make one of those 5-byte jump rel 32s. And this is FFFFFE3E, which is jumping back 450 bytes. So that will jump back to where we can have the real shell. And this one, I'm again just using a shell. All right, and I think, yeah, here we're just going to use, I think, a fake shell here. There's the prefix. Yeah, here's the fake shell. Buffer is just break times 500. So that's SEH3. So let's see that go. It's debug, restart. Yes, and then run again. Okay, and so here's SEH3. Let's take a look at it. Okay, so here's the pivot that will jump back 4 bytes. Here's the thing that will jump back 10 bytes. Here's the thing that will jump back 450 bytes, this part here. And then it's going to hit somewhere back here in my buffer, which is full of breaks. So let's run that. SEH3. Okay, so here's the first access violation. And I enter with Shift F9, I enter the exception handler. And then it's going to run and hit an int3 back here. So here's the 6250 10B4. Here's the first hop back 4 bytes. Then if I continue with F9, I'll go back to the next one where it ran these NOPs and hit that int. This is where it jumped back 10 bytes. And the next F9, this is where now it jumped back like 450 bytes or something. So now I'm back in this long list of CCs, so I can put real Metasploit shellcode there. So it's just using techniques we already know. Now that we've seen that it's all going to work, now we just have to generate the code, so you can do that with MSF Venom. I'm using a interpreter reverse shell. You have to give it the IP address of your command and control server, which is my Linux box. And then you copy that code and you put it in your attack. And so that's just what replaces that other buffer. So that's the game. And so then I can do it with just one shell. It's just a little screwy. It might be a little easier to see if I used 2 shell windows, but I don't need them. I'll do debug, restart, and say yes. Now first I'm going to send the attack. Let's take a look at it. Here's cat SEH4. And notice I've left in these breaks. So this is not going to run. It's going to stop a few times just so we can watch it go. So it'll first do the stack pivot and then break. Then it'll do the short jump and break. And then it will run the real shell code. There's no break here. So we'll see a couple spots to see it go. So I'm going to send that to my server. Now, oh, connection refused. Well, is the address wrong? 192.168.11. Oh, no, I forgot to run it, didn't I? It's paused. Okay. It has to be running, obviously. Okay, let's try it again. Okay, so now it went and hit the first exception. Now, I'm going to have a shellcode open here, but it's a reverse shell, like you usually have to on Windows to get out of the firewall. So I have to have a handler waiting for it. So let's get that handler ready. And let's find my right window. Here we are. And so here's the code that opens the handler. MSF console, you tell it what exploit you're using, you tell it what payload you're using, and what address you're using, and that will start a Metasploit handler to receive it. So it should let me copy all this stuff at once, and so it does. Okay, now it's listening, so now I can let the exploit continue. So here I was ready to pass it with Shift F9, pass the exception in. And so now it moved to the first int. Here's the 625010B4. So it needs another F9. There's that jump. And another F9 is that jump. And it's hit another inch. There we are. The next one's working. And now see it's calling all these system calls. This is the Metasploit shellcode running, calling a bunch of API calls. And here it is phoning home. So now I have an interpreter shell. So I don't know. I can do lots of things here, like who am I think. Yep, or ID. Oh well, sysinfo. There. I'm now a Windows machine. You can see I have Windows 10. So it worked. I exploited a 64-bit Windows 10, but the code I'm running is in fact 32-bit code. That was just the code I chose in exploit. So that's the point. It works, and those are the steps you have to go through. So there's a few instructive techniques there, but it's really, you know, a relatively small improvement on the buffer overflow. And, you know, that's what I've said several times in this course. All these, it's just the basic buffer overflow and then a few additional features added to cope with Microsoft defenses. So that's what I wanted to show you.